Column-oriented storage. If you have trillions of rows and petabytes of data in your fact tables, storing and querying them efficiently becomes a challenging problem. Dimension tables are usually much smaller, millions of rows, so in this section we will concentrate primarily on storage of facts. Although fact tables are often over 100 columns wide, a typical data warehouse query only accesses 4 or 5 of them at one time. Select asterisk queries are rarely needed for analytics. Take the query in example 3-1. It accesses a large number of rows every occurrence of someone buying fruit or candy during the 2013 calendar year, but it only needs to access 3 columns of the fact sales table: date key, product SK, and quantity. The query ignores all other columns. Example 3-1. Analyzing whether people are more inclined to buy fresh fruit or candy, depending on the day of the week. How can we execute this query efficiently? In most old databases, storage is laid out in a row-oriented fashion. All the values from one row of a table are stored next to each other. Document databases are similar. An entire document is typically stored as one contiguous sequence of bytes. You can see this in the CSV example of figure 3-1. In order to process a query like example 3-1, you may have indexes on factsales.datekey and / or factsales.productsk that tell the storage engine where to find all the sales for a particular date or for a particular product. But then, a row-oriented storage engine still needs to load all of those rows, each consisting of over 100 attributes, from disk into memory, parse them, and filter out those that don't meet the required conditions. That can take a long time. The idea behind column-oriented storage is simple. Don't store all the values from one row together, but store all the values from each column together instead. If each column is stored in a separate file, a query only needs to read and parse those columns that are used in that query, which can save a lot of work. This principle is illustrated in figure 3-10. Column storage is easiest to understand in a relational data model, but it applies equally to non-relational data. For example, Parquet is a columnar storage format that supports a document data model based on Google's Dremel. Figure 3-10. Storing relational data by column rather than by row. The column-oriented storage layout relies on each column file containing the rows in the same order. Thus, if you need to reassemble an entire row, you can take the 23rd entry from each of the individual column files and put them together to form the 23rd row of the table. Column compression. Besides only loading those columns from disk that are required for a query, we can further reduce the demands on disk throughput by compressing data. Fortunately, column-oriented storage often lends itself very well to compression. Take a look at the sequences of values for each column in figure 3-10. They often look quite repetitive, which is a good sign for compression. Depending on the data in the column, different compression techniques can be used. One technique that is particularly effective in data warehouses is bitmap encoding, illustrated in figure 3-11. Figure 3-11. Compressed bitmap indexed storage of a single column. Often, the number of distinct values in a column is small compared to the number of rows. For example, a retailer may have billions of sales transactions, but only 100,000 distinct products. We can now take a column with n distinct values and turn it into n separate bitmaps. One bitmap for each distinct value, with 1 bit for each row. The bit is 1 if the row has that value, and 0 if not. If n is very small, for example, a country column may have approximately 200 distinct values. Those bitmaps can be stored with 1 bit per row. But if n is bigger, there will be a lot of zeros in most of the bitmaps. We say that they are sparse. In that case, the bitmaps can additionally be run-length encoded, as shown at the bottom of figure 3-11. This can make the encoding of a column remarkably compact. Bitmap indexes such as these are very well suited for the kinds of queries that are common in a data warehouse. For example, load the 3 bitmaps for product SK equals 30, product SK equals 68, and product SK equals 69, and calculate the bitwise of the 3 bitmaps, which can be done very efficiently. where product sk equals 31 and store sk equals 3. Load the bitmaps for product sk equals 31 and store sk equals 3, and calculate the bitwise end. This works because the columns contain the rows in the same order, so the kth bit in one column's bitmap corresponds to the same row as the kth bit in another column's bitmap. There are also various other compression schemes for different kinds of data, but we won't go into them in detail. See for an overview. Column-oriented storage and column families. Cassandra and HBase have a concept of column families, which they inherited from Bigtable. However, it is very misleading to call them column-oriented. Within each column family, they store all columns from a row together, along with a row key, and they do not use column compression. Thus, the Bigtable model is still mostly row-oriented. Memory bandwidth and vectorized processing for data warehouse queries that need to scan over millions of rows. A big bottleneck is the bandwidth for getting data from disk into memory. However, that is not the only bottleneck. Developers of analytical databases also worry about efficiently using the bandwidth from main memory into the CPU cache, avoiding branch mispredictions and bubbles in the CPU instruction processing pipeline, and making use of single instruction multi-data SIMD instructions in modern CPUs. Besides reducing the volume of data that needs to be loaded from disk, column-oriented storage layouts are also good for making efficient use of CPU cycles. For example, the query engine can take a chunk of compressed column data that fits comfortably in the CPU's L1 cache and iterate through it in a tight loop, that is, with no function calls. A CPU can execute such a loop much faster than code that requires a lot of function calls and conditions for each record that is processed. Column compression allows more rows from a column to fit in the same amount of L1 cache. Operators, such as the bitwise and ender described previously, can be designed to operate on such chunks of compressed column data directly. This technique is known as vectorized processing. Sort order in column storage. In a column store, it doesn't necessarily matter in which order the rows are stored. It's easiest to store them in the order in which they were inserted, since then inserting a new row just means appending to each of the column files. However, we can choose to impose an order like we did with SS tables previously, and use that as an indexing mechanism. Note that it wouldn't make sense to sort each column independently, because then we would no longer know which items in the columns belong to the same row. We can only reconstruct a row because we know that the kth item in one column belongs to the same row as the kth item in another column. Rather, the data needs to be sorted an entire row at a time, even though it is stored by column. The administrator of the database can choose the columns by which the table should be sorted, using their knowledge of common queries. For example, if queries often target date ranges, such as the last month, it might make sense to make date key the first sort key. Then the query optimizer can scan only the rows from the last month, which will be much faster than scanning all rows. A second column can determine the sort order of any rows that have the same value in the first column. For example, if date key is the first sort key in figure 3-10, it might make sense for product SK to be the second sort key so that all sales for the same product on the same day are grouped together in storage. That will help queries that need to group or filter sales by product within a certain date range. Another advantage of sorted order is that it can help with compression of columns. If the primary sort column does not have many distinct values, then after sorting, it will have long sequences where the same value is repeated many times in a row. A simple run length encoding, like we used for the bitmaps in figure 3-11, could compress that column down to a few kilobytes even if the table has billions of rows. That compression effect is strongest on the first sort key. The second and third sort keys will be more jumbled up, and thus not have such long runs of repeated values. Columns further down the sorting priority appear in essentially random order, so they probably won't compress as well. But having the first few columns sorted is still a win overall. A clever extension of this idea was introduced in CStore and adopted in the commercial data warehouse Vertica. Different queries benefit from different sort orders, so why not store the same data sorted in several different ways? Data needs to be replicated to multiple machines anyway, so that you don't lose data if one machine fails. You might as well store that redundant data sorted in different ways so that when you're processing a query, you can use the version that best fits the query pattern. Having multiple sort orders in a column-oriented store is a bit similar to having multiple secondary indexes in a row-oriented store. But the big difference is that the row-oriented store keeps every row in one place in the heap file or a clustered index, and secondary indexes just contain pointers to the matching rows. In a column store, there normally aren't any pointers to data elsewhere, only columns containing values. Writing to column-oriented storage. These optimizations make sense in data warehouses because most of the load consists of large read-only queries run by analysts. Column-oriented storage, compression, and sorting all help to make those read queries faster. However, they have the downside of making writes more difficult. An update-in-place approach, like B-tree's use, is not possible with compressed columns. If you wanted to insert a row in the middle of a sorted table, you would most likely have to rewrite all the column files. As rows are identified by their position within a column, the insertion has to update all columns consistently. Fortunately, we have already seen a good solution earlier in this chapter. LS entries. All writes first go to an in-memory store, where they are added to a sorted structure and prepared for writing to disk. It doesn't matter whether the in-memory store is row-oriented or column-oriented. When enough writes have accumulated, they are merged with the column files on disk and written to new files in bulk. This is essentially what Vertica does. Queries need to examine both the column data on disk and the recent writes in memory, and combine the two. However, the query optimizer hides this distinction from the user. From an analyst's point of view, data that has been modified with inserts, updates, or deletes is immediately reflected in subsequent queries.